Hello and welcome to this webinar. Thank you for taking time and to join in today. My name is Dieter Etz. I'm a research engineer and project manager functional safety at the Austrian Center for Digital Production. This is the first part of our webinar series on flexible safety systems. Today we are talking about the introduction to the topic. First, let me give you a brief overview. After an introduction of Industry 4.0 manufacturing and its relation to safety, two use cases will illustrate the challenges of the topic at hand. Then the idea of flexible safety systems is presented and the underlying concepts are explained. A quick glance at the used base technologies shall give you an insight into safety communication and its specific characteristics. Finally, a summary will recapitulate the main points of the topic. Now let's have a look at the Industry 4.0 manufacturing and why safety needs particular attention in this context. There are several requirements on machinery used for Industry 4.0 manufacturing. First, it's the idea of Industry 4.0 manufacturing is customized mass production or lot size 1 production, which means a single piece production with the cost of mass production. Then you need a flexible change of configuration, including hardware as well as software. Also, rapid change of process and product configuration is important in order to minimize setup time. Now, let's come to reconfigurable manufacturing system. This type of manufacturing system was already introduced in the 1990s, and with the emergence of Industry 4.0 manufacturing, a reconfigurable manufacturing system experiencing now a renaissance. These reconfigurable manufacturing systems are characterized by scalability, convertibility, diagnosability, customization, modularity, and integrability. Also, an important aspect is the standardized interfaces, that there are standardized interfaces, including communication. This addresses the need for interoperability among machinery. Now let me jump to a very different and also very important topic in industrial machinery: safety. There are certain standards for safety, such as the ISC 61508, which is a generic base standard for other sector-specific safety standards, such as the ISC 62061, which deals with machinery. Safety is defined for the protection of man, machine, and environment. Functional safety is the detection of a potentially dangerous condition resulting in the activation of a protective or corrective device or mechanism. And it relies on active system. It therefore differs from a passive system, such as a fence. There are many reasons for implementing safety measures in industrial machinery, and one of it is regulation. There are different kinds of regulation, such as administrative law. Administrative law deals with consequences without suffering any damage. And an example would be the European Union's Machinery Directive, which is in short time becoming a regulation. This regulation defines responsibilities of the machine manufacturer and the machine operator. It means that a machine manufacturer has to design and engineer a safe machine. On the other hand, the operator of this machine has to take care of a safe operation of this machinery. Another regulation is criminal law, which deals with the consequences after suffering a damage. And there's also the civil law, which deals with compensation, which means who is actually liable for the damage. Now let me come to the so-called overall safety life cycle. These life cycles are adopted by several safety standards, and these life cycles provide a systematic way of all activity necessary in order to achieve safety certification. It therefore provides a framework to achieve the required safety integrity level. On the right-hand side in the graphics you can see such a safety life cycle, which consists of three phases, starting with the analysis, then realization, and finally operation. And all these steps have to be executed in order to reach safety certification. You can also see there's a straight path through all these activities, and there is one way back, which is in the case of modification or retrofit of machinery, that you have to go back to the analysis and start this process all over again. This brings us to the challenges of flexible machinery in Industry 4.0 manufacturing. So what are the challenges? First of all, the reconfiguration of machinery, including the safety configuration. The operator of the machinery wants to have quick, simple and safe reconfiguration. And this reconfiguration depends on the product or on the process. Change requests therefore can originate from a human operator as well from an orchestration system. Today, this reconfiguration of safety is not really existing. There is only a way that you can use an operation mode selector to switch between a number of safety configurations. But it's not flexible as the operator wants to have it. Another challenge is the high degree of complexity of these many configurations. And this is due to the high degree of flexibility and customization of the machinery. Also, the high degree of complexity is due to the rapid rearrangement of modules of machinery. And this includes hardware as well as software modules, and in our case also safety devices and safety configuration. And there are many layers of configuration, also in that context, hardware, product, process or safety, which have to be reconfigured at the same time. And therefore, an assistance system is mandatory in order to provide rapid and safe reconfiguration for the operator. This means the operator will be enabled for quick reconfiguration even during operation. And for the reduction of the operator's workload and for the increased safety, such an assistance system becomes mandatory. This also has the reason to avoid careless mistakes when doing some quick reconfiguration of the system. So let me come now to use cases in order for an easier understanding of the topic. I provided two use cases which will show the need for flexibility in safety in machinery. The first use case is a flexible manufacturing cell or a flexible manufacturing line. And the purpose here is a quick and simple switching between production configuration, which means you have a flexible manufacturing cell, and this cell is operated in a different way depending on the shift, for example. So in early shift, for instance, you're using it in a manual way. The late shift has a mixed operation mode between manual and automatic, and the night shift is running fully automatic. There is also the need for a quick and simple switching between production process configuration and also the product configuration. And as you can see on the right graphics, in the flexible manufacturing line, which consists of many flexible manufacturing cells, the process can change due to a failure, for instance, of one of the machines. This means the orchestration system can automatically switch to a different path through the line, which includes also the safety configuration. The second use case is the case of a driverless transport system. In that case, quick, simple adaptation of safety configuration is necessary due to changed production process configuration, due to a different product characteristics, for instance, the size of the workpiece, or through a verified request of an automated guided vehicle. In the graphics, you can see an automated guided vehicle which arrives at a production cell, which is protected by a light fence. After a request from the HRV to the production cell, this light fence is opened up for the HRV in order to pass into the production cell. After passing through, the light fence is activated again. Now let me come to the concepts and the idea of flexible safety systems and why this flexible safety system is important for the just mentioned use cases. First, let me give you a concept overview. On this picture you can see on the bottom 3 different safety nodes or safety domains with safety equipment. These safety nodes are connected with an industrial Ethernet network, and each of these nodes has a safety interface or a safety gateway, which means these safety domains are connected via industrial Ethernet and also with a safety communication platform. On top of that, you can see a safety network controller. This is basically the heart of the system. And on the one hand, it takes over all the activities needed for network and for safety configuration. At the same time, it works as an assistance system for the operator in that way that on the left-hand side, on the top, you can see the human control interface, which is basically a graphical user interface, which is directly or via a cloud application connected to the safety network controller. And on the other hand, on the right-hand side, you can see a manufacturing orchestration, which can be an RP or MES system, which can also send requests to the safety network controller in order to change the safety configuration of the whole network. Now let's have a look inside this safety network controller. Here you can see the configuration procedure. On the right-hand side, there is a CPPS, a Cyber Physical Production System, with a safety control loop inside. And if there are any changes, any hardware changes in the CPPS, there is the blue arrow which goes directly to the discovery, which means the safety network controller automatically discovers all the safety devices which are in the machinery. Not only the devices, but also the network, the topology, how these devices are connected with each other. With this database of devices and topology, in the next step, in the safety configuration generator, a safety configuration template is produced, which in the next step can be adapted and has to be validated by the human operator. And therefore, you can see the HMI, the human machine interface of the safety network controller, where the human operator can adapt and validate this configuration. In the next step, there's also a plausibility check, which does some sanity check, such as conflict, for instance, and if this configuration can really be deployed into the existing hardware. In the next step, if this check is passed, there is an automatic deployment which takes care that all the different parts of configuration are deployed into the hardware system. This means all this deployment phase is connecting to all devices within the cyber physical production system and deploys all parts of the configuration in the correct way. What you also can see in this graphics of the safety network controller is a machine-to-machine control interface. This is for connecting an ERP or MES system to this controller, which means also the ERP or MES system can demand a specific safety configuration to be deployed into the machinery. At the bottom, you can see some necessary parts of the system, such as an information system, which is basically for data storage and data processing. On the right-hand side, you can see also a knowledge base where all the information of the system is being stored. And there is also, for future use, legal regulation stored in this knowledge base in order to be able to check if a safety configuration complies to certain legal standards or certain legal regulations. Now let's have a look at the base technologies which are used in order to make this flexible safety system possible. First, and I mentioned that already at the beginning, interoperability is one of the main aspects of safety communication within an Industry 4.0 manufacturing system. And here you can see there are four different machines from different vendors. And the idea is to use standardized communication in order to connect all this machinery. The first building block is in that context time-sensitive networking. This technology is a deterministic communication platform based on IEEE 802.3 Ethernet, and it provides time synchronization, traffic scheduling, and system configuration among other features. Basically, it's a converged network with critical and non-critical data traffic. And it's a way for a vendor-neutral IEEE standard. The second building block is OPC-UA, which is an industrial communication standard. It's platform independent, so it can be implemented from a small embedded system up to a cloud solution. And OPC-UA provides an extensible design, which means a manufacturer can extend the existing OPC-UA standards with UA companion specifications. The third building block for safety communication is OPC-UA safety. And this is safety communication based upon OPC-UA. It's certified according to ISC 61508, and it's also a vendor-neutral industry standard. So, and this brings us directly to the summary of the presentation. First, we were talking about Industry 4.0 and reconfigurable manufacturing systems and the challenges with safety. The main points there were quick, simple and safe reconfiguration, and that an assistance system is needed in order to operate such complex systems. Then I presented two use cases, one with the flexible manufacturing cells and manufacturing lines, and the second use case about driverless transport systems. After that, I showed the concepts of flexible safety system with an overview and with the configuration procedure. And at last, we are mentioning the base technologies used for flexible safety systems, and that it's a standardized safety communication platform which addresses the need for interoperability in an Industry 4.0 manufacturing system. These base technologies were time-sensitive networking, OPCOA, and OPCOA safety. In the next part of this webinar series, the base technologies will be explained in more detail. Attention will be focused on how to realize vendor-neutral, standardized and certified safety communication in order to enable interoperability among machines from various manufacturers. This concludes part 1 of our webinar series on flexible safety systems. Thank you for your attention and watching. Visit us also on social media and stay tuned for the upcoming parts of our webinar series.